Hi everybody, I hope this video finds you well. In today's video, we're going to be continuing on with our investigation of different mathematical proof techniques by talking about what is called proof by contradiction. Now, if you've been following along with these videos so far, we've already talked about direct proof and proof by contrapositive. A proof by contradiction is yet another sort of logical approach to attempting to prove a mathematical statement. So, just like we've done in the previous ones, we'll quickly discuss what a proof by contradiction actually is, and then we'll look at a couple of examples of writing out a proof by contradiction. So, a proof by contradiction is a mathematical proof where we begin our proof by assuming the negation of what we are trying to prove. We then proceed directly from this additional assumption and arrive at a contradiction. So before we talk about why logically this works, let's think a little bit about exactly what this process is going to be like. So if you attempt a proof by contradiction, the first thing you're going to do is you're going to assume the negation of what you're trying to prove. So you have some sort of goal in your mathematical proof, you have what you are trying to prove, and you are going to assume the opposite or the negation of that. So we're going to start from assuming the opposite of what our goal is. We are then going to proceed directly. So again, we'll proceed from that assumption using either logical steps, mathematical operations, known properties, whatever sort of pieces we want to take step forwards until we arrive at a contradiction. And a contradiction means that we arrive at something that is nonsensical, that we know is not correct. So we start by assuming the opposite of what we're trying to prove. We then work along through a series of steps and arrive at something we know is incorrect. We arrive at a contradiction. Now, the reason this works is because once we arrive at that contradiction, this means that that additional assumption we made, which remember was the negation of our actual goal, must be false. And we know this because we arrived at a contradiction. So we ended up somewhere that we know is logically incorrect. We only made one additional assumption. That additional assumption must be what was incorrect. In other words, you can sort of think about it as you're walking along, you decide to make one particular decision, one turn down a route. That route leads somewhere terrible, and then you know that it was that turn down that route that led you to something terrible because you only added that one additional assumption. So we've taken that additional assumption. That was the negation of our actual goal, and now we know that that must be false because it led us somewhere terrible. The negation of our goal being false, well, that is logically equivalent to our original goal being true, right? If the negation of our goal is false, well, that means that our original goal is true, right? That's the concept of like a double negative there. So since we now know that our original goal is true, that will mean that we have proven the desired result. So in other words, what we do in this proof by contradiction is we assume the opposite of what we are trying to prove, follow along until we reach that contradiction. Once we arrive at that contradiction, we realize that that assumption of the opposite of what we were trying to prove is incorrect. So what we are trying to prove then must be correct. Now, a couple notes about this. Again, as we do our examples in this video, you sort of know that we're going to be using proof by contradiction. Oftentimes when you're first working on proofs in different sort of classroom settings, sometimes they'll just tell you to use a proof by contradiction. But in general, as you develop your comfortability with mathematical proof, we do want to be thinking about what helps us identify when a proof by contradiction might be useful. So two quick notes about this approach. First, a proof by contradiction is a bit broader than a proof by contrapositive. And this doesn't necessarily mean that this is broader in like a purely logical sense, but in terms of like an application sense, at least at the introductory level. Keep in mind that that contrapositive is much easier to do when we have something that is written as a if P then Q type statement because we need to go ahead and find that contrapositive. The proof by contradiction doesn't really require quite that strict of a format as long as we are able to negate the goal, negate whatever we are trying to prove, then you can go ahead and use a proof by contradiction. So there are some instances, at least at the introductory level, where the sort of way that the statement is written out is a little bit easier to do a proof by contradiction than it is to do a proof by contrapositive. Also, similar to a proof by contrapositive, a proof by contradiction works well when it is easy to negate our goal. And what we mean by easy is, well, it should be pretty logically clear how we plan on negating our goal. If it's going to be complicated logically to negate the goal of our statement or where we are trying to go in our statement, then that's going to make the contradiction a lot harder to do. So we want it to be an easy thing to negate. And also, hopefully, it'll be sort of useful once we negate it, right? It'll be more concrete. We saw some examples of that when we did discuss like contrapositive, where sometimes when we did the negation, we got a statement that was more easy to sort of work with, that was more useful, that gave us more information. Same thing with proof by contradiction. If the negation of what we're trying to prove is a more concrete, information-heavy statement, then that might mean that proof by contradiction is a good choice. So let's go ahead and look at a couple examples. And our first example is going to be sort of interesting. It's actually one of the examples we've already done when we did proof by contrapositive. We actually proved this statement already in the previous sort of video here. This is going to demonstrate, well, first, how you do a proof by contradiction, but it should also sort of remind you that there isn't really this idea that there's only one way to prove things, right? A lot of times these different mathematical statements can be proven in a bunch of different ways. They're all equally valid. It's just more up to you, if you were sort of doing it, which one you sort of identify, which one makes more sense, and so on. So for this, we're going to once again prove that if n squared is even, then n is even. So we're going to go straight in and do this as a proof by contradiction. Now, for a proof by contradiction, we are of course going to keep the original assumption. So we are assuming n squared is even. Now again, we are pretty aware of what that means. That means that there exists some k, an element of the integers, such that n squared is equal to 2k, right? We know that. And now we're going to do the contradiction part. Our goal is to show that n is even, so we are going to assume the opposite. We're going to do this extra assumption, right? This is the extra assumption that's necessary in the proof by contradiction. We're going to assume n is not even. And, well, notice that here, that's the negation, right? The negation is not even. But luckily, this is an easy thing to negate because not even has a nicer meaning, right? This directly implies that n is odd. Okay, so we've taken our original assumption. This is just part of what we have, n squared is even. And then we've gone ahead and started the proof by contradiction by going ahead and assuming the negation of what we're trying to show. We're trying to show n is even. We're going to assume that it's not even. Lucky for us, not even has a nicer name. It means n is odd. Now we're going to need to do some work and hopefully arrive at a contradiction. And a contradiction is anything that is a nonsensical or untrue statement. So if we arrive at something like 1 equals 0, that's a contradiction. If we arrive at something where we work our way down and we get that n is even, that would be a contradiction because we just said n is supposed to be odd. If we work our way down and we end up getting n squared is odd, then that's a contradiction because we assumed n squared is even. Anything that we arrive at that we know is incorrect is a contradiction. So let's go ahead and start, just like we said, let's start with this extra assumption that we're doing here. So n is odd. So we know that that means, right, that tells us that there exists, we won't use k anymore, I guess we'll use like m. There exists an m, an element of the integers, such that n is equal to 2m plus 1, right? That's the definition of being odd there. Okay, so we have that n equals 2m plus 1. Well, we know some stuff about n squared, so let's go ahead and construct n squared from this. Let's go ahead and square both sides. So n squared is 2m plus 1 squared. And if we just move down here, right, we have n squared. I'm going ahead and just squaring that out, 4m squared plus 4m plus 1. And then we can do a little bit of factoring. We can see that n squared is, 2 times 2m squared plus 2m plus 1. Oh, and I guess we can go ahead and do a little bit of definition. We've already used like m and k. I guess we can just use like r. So let r equal 2m squared plus 2m. And notice that we have n squared is 2r plus 1. Now, what does this tell us? Well, we know that this means, right? This tells us, so n squared, well, this is the definition of being odd. So n squared is odd. But that is a contradiction. Why is that a contradiction? Because we assumed that n squared is even, right? That was something we're originally given in our statement, so we are assuming that that is true. We've followed this logic, and we've arrived that n squared must be odd. That contradicts n squared being even. So this contradicts that n squared is even. Okay, so that must mean something was wrong. We're not going to say this assumption is wrong because that's part of the given of our statement. Well, what must be wrong then was this extra assumption that we made here. This extra assumption that n is not even, aka that n is odd. So we know that this extra assumption must be incorrect. In other words, right, the original assumption must be correct, right? So we could say thus, n being not even leads to a contradiction, right? That was the additional assumption that we had made there, and being not even leads to a contradiction. So n must be even. And that was what we wanted to prove, right? We wanted to prove that n was even. We showed that if we assume that it's not even, it leads us to a contradiction, and therefore n must be even. That is our proof by contradiction. Now, you can think, and it depends really on your sort of personal opinion here, whether or not this was better or worse than that proof by contrapositive we did in the previous one. I personally think they're actually quite similar in this case. In terms of the work, they both hinge on sort of looking at n, squaring it, and recognizing the relation between n and n squared in terms of parity. But some people prefer the contrapositive here, some people prefer the proof by contradiction. Notice that one thing that is important in the proof by contradiction, right, we're not negating both statements and reversing it. We're keeping any original assumptions the same and only negating what we're trying to prove. Then we proceed from that new assumption. Normally, we're not allowed to assume what we're trying to prove, but we're assuming the negation of what we're trying to prove. And then we proceed forward until we arrive at some contradiction. Okay, let's try this on something else, something that actually we wouldn't really have a clear way to do it through the contrapositive, but it works very nicely with contradiction. So, for our second example, we're going to prove that there is no smallest positive rational number. So in other words, we're going to sort of show that there is no smallest positive rational number. Okay, so obviously that doesn't mean that we're not looking at something like 0, we're not looking at something like negatives, right? We're saying that there's no smallest positive rational number. Now you can see in this one why this is a bit harder to imagine if you try to do contrapositive. It doesn't have that nice if-then statement where we would be easy to negate and reverse. But it does have a really nice setup for our contradiction. Our goal is to show that there is no smallest positive number. So let's go ahead and look at this, right? That's our goal. There is no smallest positive number. Let's assume that the opposite of this, there's a really nice clean opposite. The opposite of no smallest positive number is that there is a smallest positive number. So we're going to assume, let's just make mention first that we are doing a proof by contradiction. Always good to sort of note what method you're doing. Not necessary, but again, just good habit. So we're going to try proof by contradiction. We're going to assume there is a smallest positive rational number. Let's let this be r. right? So we're going to let r be the smallest positive rational number. So we can just make a note. R is, if you want to use some fancier notation, it's an element of the rationals with a little plus sign just saying the positive rational numbers. So let this be R. So we're going to assume that there is a smallest positive rational number. Okay, but then go ahead and let's consider R divided by 2. Okay, so we're going to take whatever the smallest positive rational number is, and we're going to divide it by 2. Now, clearly, if we divide it by 2, R divided by 2 is less than R, right? If you cut a positive number in half, it is going to be smaller. Further, right, R over 2 is still rational. Now, this one, I think you could argue about whether or not you need to sort of justify or prove that in itself. I think most of us would agree that if you take a rational number, remember a rational number just means that it can be expressed as a quotient of integers, that if you take a quotient or a fraction and you divide it by 2, it will still be a quotient or fraction. If you want, I'm just going to write off to the side a little justification for this. Sometimes you sort of do that, right? Sometimes if you're unsure if you need to do that part of it as a formal proof, you could have it as an aside. Sometimes in like mathematical textbooks, they would have that as a lemma, so they would do it ahead of time so that you know that this step is justified. Again, it really depends on the sort of situation. Keep in mind here what we would say is that R is an element of this. What that means is that there exists P and Q, elements of the positive integers, right? We can assume that they're positive integers here, such that R equals P over Q. That's what it means to be a rational number. So R over 2 is P over 2Q, which then if we just go ahead and let, I don't know, let's call it Q prime equal 2Q, then R over 2 is P over Q prime. And then notice that this fits the definition of what it means to be a rational number. So R over 2 is an element of the rationals. And I should have put my little bolded Q there. Right, there we go. So this would be a quick justification for R over 2 is still rational. Some people would say that's probably unnecessary. We sort of know that that's the case. If you were in a really introductory sort of proofs class, they would probably say you should go ahead and prove it. Again, that's more up to the individual sort of situation. There we go. We've justified it. Okay, now back to our main flow. We've assumed that R is the smallest positive rational number. We're considering R over 2. Clearly, R over 2 is less than R. Clearly, R over 2 is still rational. So this would mean, well, this is a contradiction since R is supposed to be the smallest positive rational number. So this is a contradiction because we assume that R is the smallest positive rational number. We just created a smaller one, R over 2, smaller and still rational. So it's a smaller positive rational number. That contradicts R being the smallest one. So that's our contradiction. So where did we go wrong? Well, we must have gone wrong when we made this additional assumption. So, right, that tells us. So there must not be a smallest positive rational number. And that's what we were trying to prove. We basically showed that if we make the decision that there is a smallest positive rational number, it leads us to a contradiction. That must mean that there actually isn't one, which was our goal all along. Notice in this one here, right, you end up actually leading to a contradiction based on the same assumption. That is totally fine. Here in our first one, we made this extra assumption and then we ended up contradicting the other assumption. And like I said, also, sometimes you'll go through these and you'll come to a contradiction that isn't based on either of the original assumptions. It literally just is some contradictory statement, like you arrive at something like 0 equals 1. That is also a contradiction, and that tells you that that extra assumption you made must be incorrect. And if you've set up your proof by contradiction correctly, that will have logically proven what you were trying to do. So this brings us to the end of this proof technique. In sort of mathematical proof, these three things, direct proof, contrapositive, and contradiction, are your three main logical processes for writing out a mathematical proof. In our next video, we will talk about a very special type of mathematical proof, which is proof by induction. It is a proof technique, but it is really sort of a specialized and, well, very powerful, but very specialized sort of approach, very useful in very specific situations that often involve sort of a mathematical index. So really, that'll be sort of transitioning away from these sort of core logical approaches, right, which you should always be thinking about as direct proof, contrapositive, and contradiction.